Thank you so much for showing up. 5:30. There are plenty of options in Las Vegas. But apparently you chose to listen to TensorFlow talk, so I tip my hat to you. So my name is Julian. I'm a tech evangelist with AWS, and I focus on machine learning. In this session, we're going to talk about TensorFlow. We're going to talk about SageMaker and how to best run TensorFlow on SageMaker. And I have a pretty extensive demo to run as well at the end. So who's already using SageMaker today? All right, a few people. OK, who's already using TensorFlow today? All right, a few people too. OK, so hopefully there's something for everyone here, whether you already know SageMaker or not, and whether you already know TensorFlow or not. So that's what we're going to do, a very quick overview of SageMaker, a very quick overview of TensorFlow, then putting the two together. And I tend to believe interesting things happen when we mix those two technologies. And then I'll go through a pretty extensive demo where I will train a Karis script using a custom container, and we'll do hyperparameter optimization and all kinds of things. Okay? And of course, we'll share some resources for you to get you started. And I will stay for as long as I need to answer all the questions at the end. And of course, you will get the video on YouTube in the next couple of days. So let's start with a quick recap of SageMaker. So SageMaker was launched at re:Invent last year. And it's trying to do one thing. It's trying to help all of you out there, developers, data scientists, and whether you're machine learning experts or whether you're just starting with the thing, it's trying to help you get from experimentation to production as fast and as seamlessly as possible. So we're trying to tear down all those walls that make machine learning projects complicated. Okay? And again, whether you're an expert or whether you're just a newbie when it comes to machine learning, you'll find that SageMaker lets you do that. I have to mention SageMaker is part of a free tier, so you can use it up to a certain level, totally for free for several months. Okay, so if you've never tried SageMaker before, I recommend that you try it. And of course, I'll share some resources at the end to help you do that. So SageMaker is really it's a collection. Under that SageMaker name, we find different things. We find different modules, so to speak. So the first one deals with building stuff, right? And it's the dev environment story all over again. If you want to embark on a machine learning project, you need a sandbox, you need a server, maybe a GPU server, and you need to set it up with all the deep learning tools and the Jupyter notebooks and everything else. So it's a drag to do over and over again. And if you have large teams, it is extremely painful. So we provide notebook instances, and that's what I'm using today. Some fully managed EC2 instances pre-installed with everything that you need. And then to help you build even faster, there's a collection of built-in algorithms. And these solve typical problems like linear regression, clustering, classification, but also some more advanced stuff like time series, natural language processing, etc. So today we have 16 algos, 17 actually, because one was just added today. And again, I encourage you to start from those. Maybe your machine learning problem is close enough to what one of those algos can do, and you'll save a lot of time by not writing machine learning code and using directly one of those algos. We also provide built-in environments for machine learning and deep learning libraries. So MXNet, Chainer, TensorFlow, Python, and I think more are coming. I saw more notebooks being pushed to GitHub today with scikit-learn and SparkML. So probably that's going to be announced pretty soon. But you could really bring anything to SageMaker, and that's what I'm going to do today. I'm going to build a custom container to use Karis in here. And then once you are happy with your algo, with the model, you want to train it, you want to optimize it, and SageMaker provides very simple APIs to train at any scale. So one API call, as you will see, fires up a training cluster, and you get the model back. And literally one API call fires up an automatic model tuning job to figure out what the best parameters are, et cetera, et cetera. So you really spend no time messing with the lower level details. You really focus on the machine learning task. And we'll see all of this in a moment. And once you're happy with the performance, the accuracy of the model, then you can deploy it. Okay? And again, it's really one line of code thing. There's a deploy API that deploys your model to a fleet of web servers that are fully managed by SageMaker. You can implement auto-scaling if you'd like. And those web servers will serve HTTPS predictions to your apps. You can also do batch transform if you have no need for HTTPS-based prediction. So you can transform in batch mode your data set and get your result back in S3. Okay? So different ways of predicting. So SageMaker, like I said, was released last year. It is really popular, so it really seems to solve the pain points that the customers ask us to solve, making machine learning agile, making machine learning free of infrastructure problems. And we have lots of customers. And it's an interesting mix of, I would say, large enterprise like GE, Dow Jones, Intuit, et cetera, and big web startups, and small ones too, right? So people who have either tons of enterprise data or people who have tons of web and mobile data, and they want to run all kinds of machine learning models. Okay, so if you're interested in those, you can just you can go to the SageMaker service page, and you will find lots of information on those use cases. But it's really it's really for everybody. It's not just for the big machine learning experts or for the super crazy startups out there. Everybody seems to find something that they like in here. So let's talk about TensorFlow now. So as you probably know, it's probably the most popular deep learning library out there. It's open source. The main API is Python. That's what I will use today. And you have some kind of support for other languages. The nice thing about TensorFlow is that it has built-in support for all kinds of neural network architectures. So whether you're trying to build fully connected networks, convolutional neural networks, or LSTM networks, or other kinds of networks, you have some high-level APIs to do that pretty easily. Initially, TensorFlow used symbolic execution. So symbolic execution works in two steps. You first define the model, okay? So you define the execution graph, so to speak. Then it's frozen, and then you train, okay? So symbolic execution is fast because since the graph is fully defined at training time, you can apply all kinds of optimizations. The downside to this is the graph is frozen, and it cannot be changed during execution. So for advanced use cases where you would like to actually modify the network during training, make it deeper, make it wider, that kind of thing, well, you can't do that. So TensorFlow has added another way of working, of training with models called imperative execution, where this time we don't have that two-phase process where we define a network and then train. It's actually all mixed. So imperative code is what we write every day when we use Python, Java, C++. So we really define and train, and we can modify the network during execution. Okay? TensorFlow calls this eager execution. Okay? And maybe one of the more popular features in TensorFlow is the Karis API. So Karis is a high-level Python API on top of TensorFlow, and it makes it very, very easy and really fast to build models. It has very, I would say, user-friendly APIs. It has great documentation. It has a lot of examples, a lot of community support, and it's really a popular choice. So let's look at a simple, basic example. In case you've never really tried TensorFlow before, that's what it will like. So here I'm using a toy data set called MNIST, which is, as you can see, a collection of digits. And the name of the game is to classify the digits in those 10 categories. Okay? So this is the full code. I mean, nothing's missing. You could copy-paste this to your laptop, and it would work. So import TensorFlow, grab the MNIST data set from TensorFlow APIs, just normalize the pixel values who are normally between 0 and 255. So bring them back to the 0, 1 range. Okay, that's good practice. And then define a simple, fully connected network where we start by flattening the image into a vector, okay, because fully connected networks have flat input layers. And then I have a first hidden layer with 512 neurons activated by the ReLU function. Then I apply dropout, which is a way to combat overfitting, to slow down training and to avoid learning too well. And then an output layer with 10 neurons because I've got 10 classes. And this one is activated by the softmax function because I want those values to look like probabilities. So all those 10 values should add up to 10 for a given picture. And then I compile the model. I use the ADAM optimizer, which doesn't require a learning rate. It figures out the learning rate automatically. I define a loss function. Here I want to build a multi-class classifier, so I use that sparse categorical cross-entropy function. And the training metric here should be accuracy. Okay? And then I just train for 5 epochs. Why not? And then I score the model against the test set. Okay, and that's all it takes. Okay, and this is really basic, but this gets to decent accuracy. Okay, so as you can see, it's not about writing tons of code. Deep learning generally doesn't need tons of code. It needs a data set, and it needs the right structure for the model, which is really the tricky thing to figure out. But the API itself, the code itself, is generally not a problem. As it happens, there's a lot of TensorFlow running on AWS. So this is a report from last year. Quite a bit of TensorFlow workloads, and Andy mentioned it again in the keynote this morning. So AWS is really the preferred way to run TensorFlow applications. And pretty happy with that. And well, unsurprisingly, we have lots of customers who are also running TensorFlow on AWS. So some of them are also SageMaker customers. You'll find some of the names I mentioned before. Some other companies don't use SageMaker. They use EC2 instances to run TensorFlow directly. Maybe they use the C5 instances or the P3 instances with the GPUs, et cetera. But again, we find all kinds of companies here. I want to give you just a quick example. So this is a company from Colorado called Matrix Analytics. And they use TensorFlow to build image recognition, computer vision models, so to speak, on medical imaging. And they try to do cancer detection, and they actually do this extremely quickly and with much better accuracy than any other kind of tool out there. And, well, that makes a difference for a lot of people, obviously. And this is all based on TensorFlow. They don't use SageMaker. They use EC2 instances directly, and they actually use the deep learning AMI, which you may have heard about. The deep learning AMI is the collection of deep learning libraries and tools and drivers, NVIDIA drivers, et cetera, completely packaged, completely pre-installed, so that, again, you don't have to wait. You don't have to deal with that. You can just focus on your machine learning task. Okay, and we have lots of customers doing that kind of thing, very, very advanced scenarios like this one. So what about putting the two together now? So, okay, SageMaker is kind of interesting. TensorFlow is kind of interesting. You know, if you mix those two together, then what happens? So the first thing that you should know is actually TensorFlow is really a first-class citizen on SageMaker, which, you know, it makes sense because it is the most popular library out there. So we provide built-in containers for training and prediction. Those containers are actually open source, so you can go and grab them from GitHub. You can compile them on your own machine, run them on your own machine to make sure your local dev environment behaves exactly the same as SageMaker will. You can customize them if you need to add extra dependencies, your own homemade libraries and whatnot. Just do that. Grab the containers, build them, modify them, push them back to ECR, our Docker repository service, and you can use them on SageMaker. Okay, so plenty of flexibility here. We support a bunch of versions. So this is the slide that is always out of date, right? So we'll keep following all the versions. And we also add extra functionality here. So actually, the TensorFlow versions that run on SageMaker are optimized for CPU and GPU. It's not just a vanilla version that you could as the one you could find out there. We actually spend a lot of time and effort optimizing them. I'll show you an example in a minute. We have distributed training out of the box, okay? And if you've tried to set up distributed training in TensorFlow manually, it's a bit of work. It's a bit of work for any library, I have to say, not specifically TensorFlow. And here, as you will see, it's as simple as saying, hey, please give me 2 instances, or 3, or 5, or 20. We have a thing called pipe mode. I'll come back to that, where we can stream infinitely large data sets to instances and improve training performance. You can use TensorBoard for visualization. You can use Karis, and you can use automatic model tuning. And we're going to cover all those things. Okay, we're going to dive deeper. This is a 400-level session, or maybe a 500-level session today. And so we're going to dive deeper on all those things. Before we do, here's I would say the basic example, right? How do you train a TensorFlow script on SageMaker? So SageMaker works with a Python SDK. It's called SageMaker SDK. And this is the SDK that gets everything going on SageMaker, training, prediction, etc. And what I like about it, it's quite high level. So we provide high-level objects like this TensorFlow object that you see here. So all you have to do, really, is create that TensorFlow object from the SageMaker SDK, pass the script, right, your Python script, which could either be Python 2 or Python 3 now, pass it to that TensorFlow object, pass a role, because obviously SageMaker needs to access S3, where your data lives, etc. Define the number of steps, define how much infrastructure you need, okay, and that's really all it takes. This is as much infrastructure as you will have to deal with when you work with SageMaker. If you want one P32XL instance with a GPU, that's all you do, right? If you need 100, just replace one with a 100, and that's all it takes. Okay, so you'll never mess with a training server again, right? Which is good news, I guess. And then pointing that estimator object, that TensorFlow object, at your data in S3, you can train. Okay, and this is strictly all there is to it. Okay, bring your TensorFlow script, which needs to implement obviously some standard functions, but this is really the standard TensorFlow way. So unless you didn't follow the TensorFlow conventions, chances are your script already implements the model FN function and the train input function, et cetera, et cetera. So really, you can take that script. It's really lift and shift for TensorFlow, right? Take that script, pass it to that TensorFlow object, and train. Okay, no modifications required, no infrastructure work required. Okay, great news. So I mentioned optimization, right? So let's look at this first example. So this goes back to beginning of the year, but it's still very relevant. So here we're training multiple computer vision models, so image classification models with TensorFlow. Okay, so ResNet 50, ResNet 152, et cetera, et cetera. And we tried 2 different configurations. So the blue bar is the vanilla TensorFlow binary, right? Is what you get if you just grab the vanilla TensorFlow package out there, okay? And we get those results, okay? If we take the TensorFlow version that has been optimized, that is available in the Deep Learning AMI and in SageMaker, you get the orange bars, okay? So the bottom line is you get 5 to 7x speed up, okay? And this is really significant because it means if you had a large model that you were training for 7 hours, now you can be down to 1 hour, which means that in a workday, you could be training many more models. You could be optimizing and trying different configurations and getting to the best model faster, okay? So this is really, really significant. This is a more recent example where we trained a ResNet 50 model, so again, one of those image classification models, on the optimized build for TensorFlow 111, so the latest version. And we used a C5 18XL instance, so this is the CPU-based instance, one of the bigger ones. And these times we're 11 times faster. Okay, so we keep optimizing, we keep improving how TensorFlow runs on our EC2 instances. Okay, so those speedups are super significant. Okay, super significant. If you train 11 times faster, then maybe you don't need to train on a GPU, right? Maybe it's fast enough to train on that large C5 instance. Okay, so it's fast, and it's probably a little more cost-effective than the large GPU instance. Okay, so you get to pick what your cost-performance ratio should be. The next thing you could try actually is not train on an EC2 instance at all. You can use local mode, which basically will train on the notebook instance itself. Okay, so the notebook instance itself is fully managed, but maybe you're experimenting, maybe you want to go fast, maybe you want to iterate fast enough, and you don't want to fire up training clusters. So you can use local mode and just obviously save time and money by not firing up the training instances. And all it takes is to use that special instance type called local, okay? And you can train on your notebook instance. Okay, very, very useful for experimentation. If you want to do distributed training, okay, like I said, the only change is to pass the right value to that train instance count parameter, and that's all there is to it, right? 2, 4, 9, 200 instances, that's all it takes. Okay, that's all it takes. So you can set it up super easily, right? No fuss. This is much, much simpler than having to set this up manually. You should try it once. You'll know what I mean. Then what if you have infinitely large data sets? And well, that's a weird way to put it, okay? So let me explain. The default way for SageMaker to train on your data is to copy the data to the training instances, okay? So if you have small and medium-sized data sets, I guess that's okay. You have enough storage on the training instances. It doesn't take much time to copy that from S3 to the instances, so why not, okay? So it could be fully replicated. It could be sharded, but okay, there is a copy involved. Now, imagine you have data sets in tens of terabytes, hundreds of terabytes, maybe more. And if you're working with huge speech or video data sets, that's going to happen. So, of course, you'll never have enough space, and the time that it would take to copy to the instances would just be silly. So to solve that problem, we came up with pipe mode. And pipe mode is a way for you to stream the data set to the instances. So the two benefits are, obviously, you're not copying anything, so training starts faster. Okay, the second your training instance is up, it starts receiving data, so it doesn't have to copy stuff. And there is really no limit to the size of the data set that you can use, because again, it is streaming. So it doesn't really matter how much storage you have, it doesn't really matter how much memory you have on that instance. It will receive batches of data, and it will just process them one after the other. And if it needs to go this way for 2 petabytes, then so be it, right? How complicated is it to set it up? Well, not much. Input mode instead of file, which is the default mode, should now be pipe. Okay, and TensorFlow supports this out of the box. Okay, so if you have large data sets, no worries. Okay, if you're working with TF record files, this is what you would do. So again, let me explain. Imagine you have a data set with 10 million images, okay, and you want to train on that. It would be 10 million files, okay? So it's not practical to live with 10 million files. It's not practical to load them. It's not practical to copy them. Everybody hates having 10 million files. So what you usually do is you use the TF record file format, which packs the different samples, the different images into files that have a record structure. And the benefit here is, obviously, you have fewer files, but possibly one single file containing all the data set. And since it has a record structure, it's easy to split, right? Which obviously is what you want to do if you are going to distribute it and stream it to different instances, okay? So this is what you would do. You need to work with this pipe mode dataset object from the SageMaker SDK. And The only change, I guess, would be in the train input function. So the train input function is the function that provides access to the training set for your script. Okay, so instead here of just reading files locally from the local file system, as you would do if the data set had been copied locally, you just iterate through that data set, fetching samples batch by batch and returning them to the model for training. Okay, so not a lot of modifications here. Okay, so we have different ways to train. Now we want to see what's going on while we train, and there's a very nice tool called TensorFlow Board. And TensorFlow Board is really, it's a visualization tool that lets you visualize training metrics. And here are some examples. We see the training loss, and these are the x-axis is the number of steps. We see the training accuracy. We see the learning rate, if we have a learning rate scheduling happening over time. So you get access to all those metrics. You can also visualize the graph. So you can actually visualize the TensorFlow graph that has been built, so the model itself. So it's a cool tool. It's super easy to set up on SageMaker. As you can see, all you need to do is pass this parameter, say, hey, please run TensorFlow Board locally. And then you point your browser at port 6006 on your notebook instance. And voila, as we say, you open TensorFlow Board and you can visualize your metrics and the model and understand if training is going well or not. Okay, super nice. There's another way to visualize training metrics in CloudWatch now, and I will show it in my demo. So, okay, we're happy with the model. Now we want to deploy it. How complicated is that? Well, not much is the answer again. So you have two scenarios here, depending on whether you train the model on SageMaker or not. Okay, because like I said, SageMaker is a collection of modules, so it's totally okay if you trained your model on your laptop or on your on-premise server and you want to deploy it on SageMaker. Okay, so you don't have to do everything on SageMaker. Just pick the bits that solve your problems and use them. So, assuming you trained on SageMaker, okay, so you would have used that TensorFlow object, that estimator object, like we've seen before, trained it. And then you would just call the deploy API, passing just a number of servers that the model should be deployed on, and the instance type. Okay? And again, if you need to deploy to 50 web servers, just say 50 instead of 1, and that's about it. Okay? You could have a slightly more elaborate configurations with auto-scaling and multiple models per endpoint to do maybe canary or green-blue deployment. Okay? But it doesn't get much more complicated than this anyway. If your model comes from outside, okay, then again, just copy it to S3, use the TensorFlow model object to load it, and just call deploy exactly in the same way. So as you can see, really, I would say the entry cost to SageMaker, if you already have TensorFlow running, is super low. Right? It's not like you're going to need to rework everything. It's not like you need to throw away the code and rewrite it. Chances are you don't need to change anything in the script itself, and you're just going to use the SageMaker SDK to orchestrate training and tuning and deploying. Okay, so it's very, very developer friendly, if you ask me. What about Karis? So Karis, as I've mentioned, is a really, really popular API. It actually supports multiple backends. So initially TensorFlow, Theano, and now Apache MXNet. Okay, so it's actually an interesting thing to try. As a side note, you just need to change one line in the config file for Karis to say, hey, please now use MXNet instead of Theano, okay, or TensorFlow, and you can compare. So actually, the Karis library, so to speak, comes in two flavors. So TensorFlow has native support for some of the Karis API, so tf.karis. So you saw those layers in my MNIST example before. So the layers themselves are accessible in TensorFlow. But if you want to use the Karis itself, the Karis library itself, which has extra features, you know, a model zoo and all kinds of very, very useful APIs, then you have to build a custom container. Okay, so I'm hoping and I'm pushing for a native Karis container, but okay, not there yet. Maybe it's going to be announced tomorrow, and I don't know, who knows. But for now, we'll stick to the custom container. And whenever I say that, people go, oh, no, I don't want to do that. You know, I don't want to build custom stuff. And as you will see, it is not difficult at all, right? It's, you know, custom container sounds daunting, but no, it isn't. As you will see, the Docker file is super short. So you need to write that Docker file or reuse mine, build a container, push it to Amazon ECR, and just train and deploy exactly in the same way. Okay? So if you want to see that full thing end to end, I have an online video showing you that, where I really go through each and every step in detail. I will go a little bit faster during my demo, but okay, you can go back to that video if you need all the steps. Okay? And one of the, actually the last thing I want to talk to you about, I want to talk about before diving into the demo is, of course, DPlans. DPlans was launched last year at reInvent. And initially it supported MXNet models, but pretty quickly we added TensorFlow support. So you could train a TensorFlow model in SageMaker, let's say, or you could use the pre-trained model. And you can very easily deploy that computer vision model to DPlans and build all kinds of funny things, okay? So you can grab any architecture listed here, ResNet or VGG or anything. Take a pre-trained model or fine-tune your model on SageMaker and use Greengrass to deploy the model and the Lambda function running inference on the camera. And it's pretty easy, right? And you can do all kinds of funny things with DPlans. Now you're all familiar with it. Okay? So now it's time to go into the demo. So we're going to do lots of things here. So it's good that I have plenty more time. And I want to show you a mix of things. So I want to show you, obviously, how to train Karis on SageMaker. Okay? So building a custom container. How do we pass hyperparameters from SageMaker to Karis? How do we get training metrics in CloudWatch? But I want to show you maybe some cool Karis things as well. Like how do you set up image augmentation to make the model even more accurate? How do you define callbacks for early stopping? So avoiding training too long. You know, if your training doesn't improve anymore, there's no point going on, so you want to stop. And checkpointing, which saves the model after each epoch, so that once you have stopped training, you can figure out which one is the most accurate one and go and grab that model. Okay, so we're going to do that first. And then we're going to focus on optimizing that script. Okay, so using automatic model tuning to run optimization on a bunch of hyperparameters. And I went pretty wild on that one, as you will see. We're going to define a custom metric as well to report how well we're doing on that tuning. We have a custom callback, and I'm going to show you how to plot results. Okay, so plenty of different things in here. So let me switch to the other machine. Okay. Did we switch? Can you see that? Yeah? All right. Okay. That worked. All right. So maybe a little bit of context first. So what we're going to do here, we're going to build a simple convolutional neural network. And we're going to try to learn a data set. So I'm not going to use MNIST, to the relief of everyone who's getting really, really tired of MNIST. I'm going to use actually another data set called Fashion MNIST. And Fashion MNIST is a drop-in replacement for MNIST. So it has 10 categories, images have the same size, et cetera, et cetera. It was put together by a company called Zalando, right? So, and the categories, as you can see here, are clothes and shoes, et cetera. And it is It is a pretty challenging data set, unlike MNIST. Okay? So these are some of the samples that we're going to try and classify. OK, so let's get started. So first of all, obviously, I need to import the SageMaker SDK. And hopefully, everybody can read this. Yeah? It's all good? All right. OK, let me know if I need to zoom in a bit. So I'm going to import the SDK. I'm going to grab the role. I'm going to grab my account number and a few more things, the region name. I'm going to need all that stuff later on when I want to push my Docker image to ECR. OK? So here's the part that's supposedly so scary. And you're going to see it's not scary at all. Even if you don't know Docker, you're going to figure it out in no time. OK, so I'm going to create a file called dockerfile.gpu because I want to enable GPU support. And this is what that file looks like. That's the scary thing. How many lines is that? I mean, you can count. It can't be more than 12 or 15 lines. Yeah, this is all it takes. So building a custom container for SageMaker is not more complicated than this. So what do we do here? We start from an existing image from NVIDIA that embeds already all the NVIDIA drivers, all the CUDA programming environment. Okay, that is rather difficult to install manually, I have to say. So it's very good that we can reuse that NVIDIA image. Then, and it is an Ubuntu-based image, OK? So I'm running apt-get to update packages, make sure I've got the latest Python, install a version of TensorFlow that supports CUDA, OK? Install Keras, clean a little bit. And then I just copy my script, which I'll show you in a minute, OK, called mnist.cnn, mnist_cnn.py. Copy that inside the container, and it should be, well, actually, it must be called /opt/program train. OK, that's the entry point. If you don't use that name, that SageMaker doesn't know what to invoke. OK, so I'm copying it with the right name, with the right permissions, set some path and environment variables. Done. OK, so no one should be scared of building their own container. If you want to build if you use R, anyone using R? All right, well, OK. If you need to build a container to run R script on SageMaker, it's going to be the same, right? So nothing scary. I think we even provide an example on GitHub. If you have your super fancy custom secret C++ library for training or prediction, OK, well, just build a container and run it on SageMaker as well, OK? Any kind of machine learning workload can run. So don't let that custom thing stop you because it's really, it's not scary at all. OK. So we will look at the script in a minute. I just want to show you all the way, get to the point where we've built a container. So I need to make sure I've got a repository in ECR, OK, for the image that I'm going to build. So define a repository name, an image name. Use the AWS CLI to create a repo if I don't have one already. OK, log into that repo, build my image. OK, so I'm using Docker build. So now I'm back in standard Docker territory. OK, so in the interest of time, I've done that. It takes a couple of minutes, but I didn't want to waste them. So after a few minutes, we have our local Docker image on the notebook instance. We tagged it. OK, we can see it here. And then I push it to ECR, again, using Docker push, standard Docker stuff. OK? And then I'm done. OK? And then I can use this container just like I would use the vanilla TensorFlow container or any other container. OK? And the last step is I want to upload my dataset to S3 because this is where SageMaker will pick it up for our training. All right? So let's look at that script, that mnist script. And all of this is on GitHub, so don't worry, you can use it. All right, I'll share it. OK, so here it is. So it's a simple convolutional neural network. OK, nothing weird. And probably a little better like that. And here I'm using a Karis, right? Karis.star. Okay, I'm not using the tf.karis API. So this is really native Karis. Okay. So the first thing to figure out is how do I get hyperparameters, right? How does SageMaker pass those hyperparameters to me? Okay, like the learning rate and more. So actually, the way this works is quite simple. The SageMaker will copy hyperparameters inside the container at startup time into a JSON file. Okay, and it has that hyperparameters.json name, which I guess makes sense. So what I'm going to do here, so I need a function to load my data, but mostly, okay, I'm going to read hyperparameters from that file. Okay, so this might be one of the things that you have to do in your native code if you want to adapt for SageMaker. Okay, depending on how you pass hyperparameters. And as you can see here, I'm reading quite a lot of hyperparameters, so obvious things like learning rate, batch size, number of epochs. But you can see, down below, I'm reading the number of filters for the convolutional layers, and I'm reading the dropout value and even the number of neurons for the fully connected layers. So, okay, we'll get to that when we do tuning, right? So this is how you read hyperparameters, okay? And the rest is really strictly Karis code, okay? It's actually one of the vanilla examples for Karis, and I didn't change anything here. The only thing that I'm doing here, obviously, is based on some of the hyperparameters, like dropout or a number of filters, I'm building the model accordingly. Okay, so initially I will use default values, but then when we do hyperparameter optimization, of course we're going to explore more. Okay, but these are the layers that I'm defining. So there is a first convolution block with pooling and dropout. There's another one with pooling and dropout, and then I have a first fully connected block here. Okay, with dropout, and then a second fully connected block. So that's what the model looks like, okay? Convolution, pooling, dropout, convolution, pooling, dropout, and then 2 fully connected layers, bringing me to the output layer, okay? So a pretty canonical example. All right, and then I'm compiling the model. I will optimize for accuracy. I define an early stopping callback, deciding that if validation accuracy hasn't improved in 30 epochs, then stop it. Okay? No need to keep training. If for 30 epochs we haven't improved, stop training. Okay? And this is the standard callback in Karis, and I highly recommend that you use it. We'll get back to the custom callback later on. And then I use a checkpointing callback to save the best model, right? Each time we have a new model that is more accurate than the previous one, then we save it, okay? And this guarantees that I will only get the best, okay? So if I have early stopping, if our early stopping kicks in at epoch 65, okay, meaning the best one was probably 30 epochs before, then I know that the model that I saved is actually that best model from epoch 35. Okay, so early stopping and checkpointing are very, very cool techniques. And then I set up image augmentation. Okay, and image augmentation is a way to generate additional samples on the fly. Okay, so you saw those fashion and this samples, but here I'm actually adding more samples during training. So I'm rotating them from minus 20 to plus 20 degrees. I'm shifting them horizontally and vertically up to 20%, and I'm also flipping them horizontally. Okay, so this is going to create plenty more samples that will slow down training for sure, because I need to train on many more samples. But this creates a more robust model because it is now facing slightly weird-looking samples, so it's going to actually help. Okay. And so I'm actually training, I have a first round of training using image augmentation, okay, for a number of epochs. And then I am training again, this time with no image augmentation, just training again with the standard data set, okay? And we'll see what that brings, okay? So there it is. That's my script. So how do we run this? Whoops. No, here it is. OK. So I mentioned earlier that you could use TensorFlow Board to visualize things, but now it's possible to use CloudWatch, actually. You can graph training metrics in CloudWatch. So obviously, you need to define what those metrics are, and this is how you do it. Define that simple dictionary with the matrix name and a regexp that tells SageMaker how to fetch the metrics in the CloudWatch log, okay? In the training log, which is also available in CloudWatch. So the regex is, OK, this is what you should be looking for. So, OK? So in the Karis log, we see those ACK loss, val ACK, val loss, and this is how to extract them. OK, so now we have everything we need to train. And since we're using a custom container, we can't use that high-level TensorFlow object like we've seen before. We use that generic training object, which is called the estimator in SageMaker, okay? And it works exactly the same. As you can see, the only difference is the image name. The first parameter is actually the name of that container in ECR, okay? So that's the Karis container that I built and pushed, okay? And you can see that name just under the cell, right? Account number .dkr, et cetera, et cetera. So that's the name that I'm using. It's the only difference. The other parameters are the same. The instance count, the instance type, the role, the output path to store the model, et cetera. OK? And now, for a first step, I'm going to set the basic hyperparameters. So I'm going to train for 100 epochs. I'm going to use 1 GPU, and I'm going to use a batch size of 256. Okay? So everything else is set to default values as defined by my script. Okay? So remember, SageMaker is going to take those values, write them to a JSON file inside the container. So once my script kicks in, it's going to read that file. It's going to find those 3 values, and it's going to use default stuff for everything else. OK? So how do we do here? So actually, I run it again. Hopefully, it completed. All right. So I trained for, again, 100 epochs with image augmentation, 100 epochs without. OK? So it trained for a total of 1,615 seconds, which is a little, I don't know, 25 minutes or something like that, right? And the best accuracy that I got is 94%, which is actually quite good for a fashion analyst already, okay? So let's visualize some of those metrics in CloudWatch. Hopefully, we can see them. And let me maybe, go back in time a bit. OK, and here I'm plotting. Can I go to maybe? No. OK, 1 hour is the best I'm going to do. OK, so I can see, so the blue line is the training accuracy, and the orange line is the validation accuracy. OK, and this corresponds exactly to what we saw here, right? So these are the metrics that I defined. So SageMaker is running the regexp on the training log and pushing the metrics to CloudWatch. Okay? And I can see that, OK, I trained for a bit, and these are probably the first 100 epochs with image augmentation, making it very difficult to learn. Okay? And then once I train again without image augmentation, then accuracy jumps pretty quickly, and we get to 94% for the validation accuracy, and something like 97% for training accuracy. Okay, so 94%, not too bad, right? And I can see the other metrics. I didn't plot them, but if I look at the loss metrics, right, accordingly, I can see the training loss going down, and I can see validation loss actually increasing. So I might have overfitted a bit. We need to check that one. Okay? So this is how you actually push the metrics in CloudWatch. Pretty easy. Okay, 94%. So, and the training log, let me just show you the log. Okay, the training log is available in CloudWatch as well, right? So you don't have to actually read it in the notebook instance. Okay. So this is good, 94. Now what about optimizing this, okay? Because I don't know, I have lots of default values here for some of the parameters. And now I want to run hyperparameter optimization on the structure itself. So I want to figure out how many convolutional filters I need in layer 1 and layer 2. I want to figure out dropout for all the layers. I want to figure out how wide those fully connected layers should be, okay? So I define all those parameters, and I define whether they're integers or continuous parameters, and I define the ranges. Okay, so for example, for the first one, I'm going to explore between 32 convolutional filters and 128 filters for the first layer, and so on, okay? And hopefully, SageMaker is going to help us figure out those values and get to improved accuracy, okay? So I still set, epochs to 100 and batch size to 256, okay? I define the metrics that I want to optimize on. So here, the success, right, the best model should be the one with the highest validation accuracy, okay? So I need to tell SageMaker how to figure out this information from the training log, okay? So once again, I need to define a metric, what the type of the metric is. So here I want to maximize accuracy, and I need to provide a regex to help SageMaker figure it out. And this is where I need that custom callback in Karis, because since I've got early stopping, I need to make sure you can't just read the accuracy for the last epoch, because quite likely this is not the best one. The best one came earlier, and then training went on for a little while because of early stopping. So I need a custom callback logging specifically the best validation accuracy for the best epoch, and this is what SageMaker grabs. Okay, and then I'm using the hyperparameter tuner object from SageMaker, passing the estimator, so that estimator for the training job that we used earlier, the metric name, the ranges, and how many jobs I want to run. So here I'm going to run 30 jobs, 3 by 3. Okay, and the way this works is SageMaker is going to train 3 models using a combination of parameters. And then each time a job completes, it's going to look at the accuracy that it gets, and it applies optimization. Okay, so it's not a random search or grid search. It's a technical Bayesian optimization where we try to approximate, we try to guess really what the next best set of parameters should be. And we make that decision based on the last few training jobs that we had. So we're going to train 3 by 3. Those 3 will complete pretty much at the same time. And then those 3 data points help SageMaker decide what the next 3 should be, et cetera, et cetera. Okay? So we're going to run 10 rounds, 3 jobs at a time. Okay? So 3 training jobs in parallel. Okay? And then we call fit to train. All right? And so this takes a while, as you can imagine, because each of those jobs takes about 26 minutes. So obviously, I prepared for this. And I should see, yes. So here's my job, actually. I can see the 30 jobs that have been trained. Okay? Yeah, so it took a while. But I'm not paying my AWS bills, so it doesn't really matter. But you should pay attention. Yeah, some people say that's the reason why I joined them, but don't listen to them. Okay? And more importantly, I can see the best training job. And I can see the best training job yielded an accuracy of 94.61. Okay? And well, remember we got 94 from the previous job, and now we got 94.60. Okay? That's a very significant improvement. And we can see the actual hyperparameters that were used, right? So I don't think anyone here would have thought of using dropout 1 set to 0.1155 or whatever. I mean, those are non-intuitive values, right? But as it turns out, based on those 30 jobs, these are the values, okay? So the dropout values and the size of the fully connected layers and the number of filters for the convolutional layers, right? These are the ones that work best, okay? So no one would have thought to use 108 filters in the first layer and 174 layers. You know, we just use power of 2. Yeah, everybody uses that 32, 64, 128, and we just pray that these are the right values. But as it turns out, these are the best ones for this tuning job, okay? So you can see all that stuff in the console, but you can also query. Let's run those cells. Yeah, so you can query those statistics. We can display those stats. Whoops. And we could plot. Okay, so this is accuracy over time. Okay, and I'm just for the heck of it, because I'm a maniac, I guess, I'm fitting a linear regression line to this because I want to see that line going up, right? I want to see the algo doing a good job at figuring out what the hyperparameters are, okay? So it has a very flat slope, I'll give you that, but there is an upwards trend, right? So you can see we are actually, model after model, step after step, we're actually going towards higher performing models, okay? So that's a good sign. And we have a weirdo somewhere. It would be interesting to look at that one. We would learn what that, probably there was a very, very negative parameter used here. We could plot accuracy versus dropout, okay? So layer 1 dropout, and layer 1 drop, CNN layer 1 dropout, CNN layer 2 dropout. So do we learn anything here? Well, I would say the higher performing models are probably the ones on the left. So that would probably mean don't use too much dropout in your first convolution layer, which makes sense, I guess, intuitively, because if you have too much dropout, then you're throwing too much information away, and then it's obviously difficult to do feature extraction if you kill too many features early on. For the second convolutional layer, it's less obvious. It's less obvious what the dropout value should be. So if you use something in the middle, you're probably safe. And for the fully connected layers, again, for the first one, there is no clear trend. So, now I understand why people tend to use 0.4 or 0.5, because I guess it's a reasonable value. For the second layer, we can see if we have excessive dropout, we have kind of lower accuracy. But again, somewhere in the middle is acceptable. Okay, and it's interesting because when you do this, you understand why all those tutorials, all those samples, they tend to use those typical values, because the guys who wrote them, they knew that, right? But now we can confirm it using hyperparameter tuning. And let's do the same for kernel filters. And so for the first layer, I guess there's a bit of a bias on the right, so something like 90 or 100 filters work best. And interestingly, for the second layer, we can see we have probably the best accuracy when we have a lot of filters, which makes sense again because in that second convolutional layer, you extract higher level features, right? You combine the low level features into higher level features, so you can have so many combinations that if you have more filters, then you can actually figure out more high-level features and more details. So that makes sense, I think. And the fully connected layers, all right? Okay, more, I guess, more interesting models on the right, right? So more fully connected neurons here help classify. For the second layer, it's not so obvious. Okay, so you could decide that, well, for the next hyperparameter tuning job, I can actually stop tuning some of these because there doesn't seem to be a big difference. So you can settle for like a median value and keep tuning on the other ones, right? Keep tuning maybe on the number of filters or keep tuning on something else. Okay, it's a highly iterative process. Okay, so there you go. And if we wanted to deploy the best model, we could do that very easily, right? Tuner.deploy, and this automatically deploys the best model. And we're happy because we have good performance. OK? So as a conclusion, we saw plenty of things. We saw what SageMaker was, what TensorFlow was, what happens when you mix both. And as you can see, there is really a lot of features on SageMaker that make TensorFlow even more efficient. Pipe mode, distributed training, et cetera, all the things that we saw. And you can still use your Tensor Board and all your favorite tools, OK? So, and it doesn't take a lot of effort to bring your TensorFlow code to SageMaker, as we saw. So if you want to get started, obviously, that's the TensorFlow and the Karis URLs. The first GitHub URL is the collection of SageMaker notebooks, okay, and it keeps growing. And there are quite a few TensorFlow examples in there, so I would recommend that you read them. The SageMaker SDK on GitHub as well, okay, with the documentation, and that will help you write stuff just like I wrote. And that's my blog on Medium if you found this session interesting and you'd like to stay in touch and read more about machine learning and deep learning. You'll find it here, okay? I want to point out we've got 2 repeats. This was the technical one without a customer. We have 2 repeats on Thursday and Friday where we will have customers on stage. So if you're interested in seeing what customers build, well, there you go. You can go and look at that one. I will not be delivering the Thursday one, but I will be delivering the Friday one. And if you want to read about a super crazy advanced use case, I really recommend the Friday session. Those guys have built something really cool. Thank you very much. I really appreciate your presence on that last session of the day. If you want to stay in touch later on, this is my Twitter handle. Feel free to ping me, ask questions, ask for guidance or whatever. Happy to help. If you're just patient, because I'm not always answering in 5 seconds, but I try to answer everyone. And if you build cool things and you'd like to share them, please, again, ping me, and I'm more than happy to retweet and share everything. Okay. Thanks again. And if you have feedback, please use the mobile app for the feedback on that session. Have a great night.